So hello, everybody. My name is Igor, and I'm a compiler technical consulting engineer at Intel. I have been working for the last 15 years here, working on making our compilers and performance as best as possible. And today I want to talk about our new wave of programming model we are suggesting to developers, to C++ developers worldwide, based on SYCL. And today I will talk about ways how you can simplify and unify the development of heterogeneous applications to target different vendors and different accelerators, such as GPUs, FPGAs, CPUs, and so on. So today we are going to talk about some basic stuff about SYCL and DPC++ as an implementation of a SYCL compiler. So we will touch high-level basic concepts like buffers, accessors, queues, kernels, and other stuff. And I will also try to explain some implementation details of Intel compiler. So at once you are ready to program something, you're picking up the right tool and setting all the required options and understanding how a compilation and execution flow is happening. And also as an example, I want to share with you one real-world application which we ported to SYCL, which is called EasyWave. It's a tsunami simulation code which allows you to calculate and emulate the tsunami waves and wave propagations. And in this case, we were able to run this code finally, one SYCL baseline code to run it on Intel GPUs, CPUs, AMD GPUs, NVIDIA GPUs, and even FPGA. So I think this is, I don't want to go into all the details about complexity of heterogeneous programming. I think it's quite well known for everyone that nowadays with a variety of hardware choices and vendor lock solutions like CUDA or other solutions which are really limiting you to use specific devices from one vendor only, it's really challenging. And also maintaining the different code paths as a result of that, right? It's really challenging. And that's why Intel and community trying to solve this problem by bringing up a great standard like SYCL, which is a Khronos-based standard, and the implementation of the compiler, which allow you to compile your SYCL conformant code to developers, so to open you all the possibilities to really unlock yourself from any limits or boundaries, right? So what's the difference between SYCL and DPC++? Because sometimes there is a confusion on why this data parallel C++ is used or SYCL. So in practice, DPC++ is the one API implementation of a SYCL. It's based on SYCL standard, and SYCL standard is based on ISO C++ standard. So it doesn't introduce any new keywords. It's a set of it's a templated library, so set of classes and APIs which you can use in your code in order to make the offloading to any kind of accelerators possible. And again, by accelerator, we usually mean any kind of device, including CPU. The final or latest up-to-date specification of SYCL is 2020, and it was published last year. And it has many improvements versus older SYCL 1.2.1 version, which was pretty much based on OpenCL by the standard. So now SYCL 2020 really removes this limitation to be based on OpenCL backend. So think about SYCL as an abstraction, right? So we want to hide the implementation details. We want to hide the details about our architecture details. And the idea is quite similar to OpenCL finally. The difference is that it's much more C++ style. It's a single source concept with SYCL, where you have both a device and host code in the same single source file. And of course, it's much more C++ based versus OpenCL, right? Again, historically, it was SYCL 1.2.1 was based on OpenCL by standard, but now this limitation is removed. Since it's abstraction, it still requires some lower level API, which is quite often called backend, to be implemented, and it should be available as a runtime library finally. And the thing is that a standard is not limiting you to OpenCL anymore. So in reality, existing implementation allow you to use CUDA backend for NVIDIA hardware, HIP backend for AMD hardware, level 0 backend or OpenCL backend for Intel hardware, and so on. So it's up to implementations to define the low level API and backend. Unfortunately, at this moment, there is no compiler on the market which can give you or provide you a full SYCL 2020 conformance, and we work hard on introducing this kind of support as soon as possible. But I think the substantial part of the support is already in DPC++ compiler, and you can always follow this link to get the up-to-date state on which exact features are supported from the standard. But the purpose of DPC++ compiler is not only to be conformant with SYCL 2020, we're also paying a lot of attention to improve the SYCL standards further. And to do that, we introduce community extensions, which are something on top of a SYCL standard. And you can find like quite many extensions already implemented by Intel. And the goal of these extensions, again, is to improve a SYCL standard. So we are bringing to a standard committee working implementation of really great features, improving usability and performance of the code. And by doing that, we are passing the review process, negotiating, improving it further, and finally making part of a future SYCL standard. So it's an iterative process. We are going here to improve finally the quality of standards itself and to hide all the gaps which we can identify. And of course, we are welcoming everyone to support this initiative and to contribute by opening on the GitHub project corresponding threads, issues, feature requests, and helping us with identification of more and more useful features which you can use. A few useful links here is, first of all, we do have Intel compiler open source. Here on the GitHub project, you can find an open source version of a compiler. And the support for all the backends which we have at this moment, like OpenCL, Level 0, CUDA, and HIP, is implemented here in the open source project. At the same time, Intel also shipping a compiler in the form of binaries, right? And we ship it as a part of one API toolkits. So there you're really getting the compiler which is targeting Intel devices only at this moment. Actually, the whole software stack is open source. So as I already mentioned, since SYCL is an abstraction, on a low level, you need some kind of lower API to be available, and also runtime to be available, right? And for GPUs, for Intel GPUs, we do have the compute runtime available as open source project too. And also, if you have some device, for example, Intel GPU, right? You need a device compiler also. And in that case, you will use for Intel devices, Intel graphics compiler, which is also available as an open source project. So SYCL ecosystem is growing, and there are many implementations available. Intel DPC++ solution or implementation is not the only one available. There is also Compute CPP shipped by CodePlay. Xilinx works on TriSYCL, and really nice implementation from University of Heidelberg called SYCL, which is in many cases even outperforming native AMD, for example, on AMD target devices. So you can find a whole range of implementations, both commercial and research projects. And this is great to see this race, and actually it's improve the quality of SYCL standards finally. So I talked, I think, too much already about the ecosystem, what is SYCL itself. So let's finally take a look on the real code to understand and to feel better why it is so nice parallel programming models or heterogeneous programming model. So the idea or basic principle of a SYCL is that you have your application, right? It's a single source application consisting of your host code and device code. So you need somehow make it clear for the compiler which part of your code is host, which will be executed on the CPU with its own memory, right? And where is the device code, which is finally submitted to a common queues via a common group and executed on some accelerator with its own hierarchy of memory, right? So note that quite often there is no direct access between CPU and device to the memory. It depends on the features, but in principle, you may introduce some feature like unifying or unified shared memory, right, to have the same address space, but you still need to transfer memory back and forth from host to device and so on. But this is the usual flow how execution of device code happens. So it uses common queues and common groups. So here you can see how it really looks like in your code. So as I said, it's a SYCL is based on C++ standard. So we don't need any new keywords. All we need to do is to include a set of header files. And we're doing it with this pre-processing directive. And then we are getting a set of classes like buffer class, queue class, and member functions of these classes to perform the submit operation and so on. So at this moment, I want to show a skeleton of a SYCL application. So here you can see that the host code, and you should also always pay attention to these markers, like the creation of a queue in the code, the queue submit operation, and parallel for invocation. So usually, if you take a look on your SYCL code, it should be quite easy to identify the accelerator device code, because it will be the code which is written here under the parallel for invocation in most of the cases. There are different ways how you can invoke the kernel finally, but this is one of the most important one and commonly used. So again, this code is going to run on some accelerator, and this accelerator may be CPU, GPU, FPGA, whatever. Also, while talking about SYCL, it's important to know application scopes and the common group scopes and device scope, because depending on where you're writing your code, you may have some limitations. So by standard, SYCL code is based on C++70, which means you may use C++17. Any compiler conformant with SYCL should have this support already. The thing is that if you write inside the device code, device scope, then you are a bit limited in which features you may use. So you cannot use the dynamic polymorphism here, or you cannot use the exceptions or asserts inside this code. So it's quite limiting you, but still you can use templates, static polymorphism, and so on. Work on improving this and relaxing some limitations is ongoing. But this is important to know that actually not all C++17 features can be used in the device scope in the kernel code. And also common group scope, it's still a host code, but there are some features which you can use only in common group scope at this moment. For example, if you want to use some device-specific features like shared local memory, for example, of GPU, then you need to create a special accessor, local accessor, and you can do it only in this common group scope. So this is important to know and separate scopes. So what about memory model? SYCL provide you in principle, two major concepts how you can work with a memory. One is based on buffers and accessors, and images is a subclass or corner case of this buffer concept, which also required accessors. So the idea is that you're wrapping your initial data which you have on the host, right, to a buffer, and then in order to access this data in the kernel, you create accessors. And the alternative way is a pointer-based concept where you're doing it pretty much like in CUDA. So you're really allocating the memory directly on the device, or you're allocating some shared memory which can migrate from device to host automatically. And then you're dealing with this pointer-based approach in your code. I will show today both concepts. There are pros and cons to use each of these concepts. So let's go further and take a more detailed look on each of the line of the code. So here I'm showing the example where we use a buffer accessor approach to deal with the memory. So this buffer memory model. So imagine we have some data on our host, right? This is usually the idea in heterogeneous world. You have some data on your host. You want to speed up the execution of some of your hotspots in regions of your code, which is spending most of the time, right? So usually, if you already have an existing code, you need to do some kind of profiling to understand in which parts of your code you have or you're spending most of the time, right? Because it makes sense to speed up these parts. You also need to keep in mind how easy it's parallelize this portion of the code, right? What's the benefit? Because you will need to transfer the data back and forth to accelerator and back. And if this overhead is too high, then you probably need to think about is it reasonable to parallelize this code with this accelerator or not? But anyway, so the idea is that you have some data, right? And you are going to perform some operations with this data on the accelerator. So you need to transfer this data to the device and back, right? Classical containers doesn't allow to do this, right? In order to do it, you need to introduce some kind of a new wrapper for your data, like buffer, or you need to use this different APIs called Unified Shared Memory we'll talk about later. So here we are constructing these buffer classes. So, okay, we have a way how to wrap the data, for example. So what's next with the queue, right? we need somehow to link to some device, right? Since SYCL is not limiting you to a hardware choice, so here it may be different devices, and you need to have a mechanism to link to different devices, and that's why you construct the queue object, which actually allow you to submit some work to a device, and you are submitting some work which is called common groups, right? So common group is all that is defined here. So common group provides kernel itself, which you're going to execute, plus the data and dependencies. So it shows you in which mode the data used in the kernel will be accessed. And in order to do this, you're actually creating these accessors. At this moment, let's talk a bit more about how you can control the device on which you want to execute this code, right? Because you see here that we use a default constructor for the queue. In that case, SYCL allow you to select the device on which you want to run this code at runtime. So there is a runtime environment variables which you can set, and in that case, you can switch between GPU, CPU, or you can also just get the list of devices available in your machine via special command, and just said, okay, I want to run on this device, even with number, right? Or you can control backend technology which you want to use in order to run. So it's very nice way how you can control it with default selectors. But if you want to do it on the source code level, then you also have this option. And in that case, you're actually just writing a CPU or GPU selector or a FPGA selector, and that's how you're limiting a set of devices which can be used to run your code, right? Or you can also create your own custom selector, and in that case, you're overloading the operator and deriving from a device selector, which is a base class. And in that case, you can create your own logic to choose the device you want. So you can, for example, get the string with a vendor name and prefer some specific vendor, right? It's interesting that if you don't specify these environment variables at runtime and you pick up the default selector, then the runtime will actually score all devices available in your system. For example, if you compare integrated graphics versus CPU, integrated graphics will have a higher score, but the discrete graphics will have a higher score versus integrated graphics and so on. So it will pick up the most performant from its point of view device and run on this device. Know that runtime, SYCL runtime, actually cares about possible data dependencies between kernels. So let me explain this situation. So imagine in this case, we are creating one common group here. And this is the kernel which we will execute finally on the device. But the important point is that SYCL by default is asynchronous execution model, which means once we do this queue submit operation method, we keep executing host code. So at this moment, we are not guaranteed that actually the execution of this kernel is already happening or finished or whatever. There are ways how to control it and how to synchronize, but in principle, you need to have this control. It's interesting, I have some kind of glitch on my second screen that's still showing me a first slide. So I hope that you actually see this slide with the code and other stuff, because it looks like some kind of bug in the Microsoft PowerPoint for me. So what happens if actually further in your code, you have one more queue submit operation, right? And you submit the other kernel, for example, kernel 2, or you submit one more command group and there it has kernel 3 and so on. Is that actually possible to execute these kernels in parallel? Yes, it is possible, and that's why we need these accessors. So we are specifying a way how we're going to access our data inside the kernel. So in this example, we are going to add elements of A and B arrays and write to C. So that's why we are reading A and B and specifying to the, while creating accessors here, we are specifying that we are going to read only through A and B accessors, and we're going to write to C. So in this case, runtime will have the information that kernel A actually writes to C. And if there will be any kernel getting C as an input, right, or writing to C, then it will wait until the kernel 1 finished the execution automatically. So under the hood, the dependency graph is built by runtime, and it cares about execution order of the kernels. However, if you will have some kernel 3, and so you will submit the common group in the same way to the same queue, which only read B, for example, right? In that case, there's no dependency or conflict between running kernel 1 and kernel 3 in parallel. So the runtime may decide to execute these kernels in parallel, right? So this is a great feature of a buffer accessor approach. It creates additional overhead, right, for you because you need to create accessors. But finally, it's also bringing you a benefit of this graph construction under the hood, because with a alternative concept and unified shared memory, you will need to do it yourself, to care about this proper execution of the kernels, which is not so hard to do, but still. So, and finally, when we invoke the parallel for method of the handler, and actually this handler is a handler to the common group. So you see that each time we create an accessor, we use this handler, because the common group has the information about all the accessors, and also we submit a kernel and invoke parallel for method for this handler. So the way, first of all, the way how we submit a common group is that we are using a lambda function here, right? So next, when we invoke parallel for, we also use a lambda function as a last argument. Before we should specify the iteration space. In this case, it's a range class, or it can be any range class. We will talk on this a bit later. And we need somehow to identify each data instance, right? Each work item inside the kernel code. So that really each execution unit of your accelerator will execute on the specific data element. So to do that, we are also creating this ID class here, or we are specifying the argument to a lambda, and it will help us to identify the data element inside the kernel code, which is called work item. Note that the template deduction feature is supported in C++ 17. That's why you can do a lot of stuff here, not explicitly specifying the templates argument, but in reality, under the hood, the range class is constructed, and moreover, this range class has a templated argument. For example, it can be 1, 2, or 3 dimensional range. So you need to keep this in mind. There are different ways how you can invoke parallel for. So one example is when you use the ID class to index the individual instance, to index the work item, right? And this is exactly what we did here when we was using auto type. So it will match to ID one-dimensional, since we have one-dimensional range. However, this ID is a bit limiting you in the features which you may use. For example, if you want to get a whole range of your iteration space inside the parallel for, in the device scope, right? There is no this method in the ID class. So you can only get it when you construct the item class. So it also represents an individual instance, but exposes additional functions, right? Where you can query different properties of execution range, for example. Now a bit few words about work items, work groups, and ND range. So you know that actually the underlying hardware is not is usually divided into some logical units, right? So it's quite often divided into some slices. The slices divided to subslices, and then each subslice consists of execution units. So in order to more efficiently use the features of underlying hardware, there are different ways of grouping available in SYCL. So again, a single thread within a thread hierarchy in SYCL and OpenCL called work item. Again, all this terminology is derived from OpenCL by historical reasons, right? Then you can combine a set of work items to a subgroup, right? In order to map it to CMD features of a hardware, for example. Work items usually, work group consisting of a set of work items, and it's quite often mapped to some logical unit of your GPU, for example. So work item mapped to execution unit, right? But work group is a subslice of your GPU, for example. And then a set of work groups builds a whole ND range, right? N-dimensional range, and it can be one dimension, as the trivial example we looked earlier. It can be two-dimensional, three-dimensional stuff. So this slide actually represents the fact that the device, and here it's integrated graphics, but more or less any vendor has, it may have different terminology, not slice, not subslice, but finally the idea is clear. So you have some units, right, consisting of a limited number of execution units, having their all fast memory, like shared local memory, for example. And it is really important to map your calculations, right, and control a way how work items build a work group and the size of these work groups. So by default, and the same for subgroups. So you can also control it to for CMD features usage. So for fine-tuning of a performance, sometimes it may be quite important to understand how many work items you have in the work group and so on. On the high level, in our example, everything was done by the compiler. So it picked up some work group size and so on. But for the real applications, it may be quite important to play a bit with the work group sizes in order to map better to the execution of your GPU. So finally, the optimization hints are quite simple, right? So what you want to do is you want to make all the execution units on the device busy with the work, right? So if you will have some kind of imbalance, over subscription and other stuff, you may hit the situation where some execution units are idle, but others are running and you are not utilizing 100% the execution units of your GPU. Note also that there is also memory hierarchy, and you can see that memory for the accelerator may be different. So it can be global memory, the largest but the slowest. It can be local memory available for each work group, which is shared between work items and not shared between work groups, which is faster than global memory. And this is one of optimization techniques. As I said earlier, to access this memory in SYCL at this moment, you need to use local accessors inside the common scope, common group scope. And there may be a private memory, so it's variables you create inside the kernel code, right, in the device scope. And in that case, they're allocated in the private memory or registers, which is the fastest but the smallest memory. So there is a way to control the mapping, right, and control the grouping of your work items by explicitly creating ND range. So in that case, you need to specify the local and global size, so-called, right, the size of the work groups. And it may help you to control the resource usage and load balance distribution. So how does it look like? So it's the same invocation of a parallel for, but you may implicitly create the ND range object here and pass as a first argument. And you can specify the global size, like here, and the workgroup size, also quite often called local size. So in this case, for our example, we are saying that our range is 1024 work items. And we want to group these work items. So the size of a workgroup will be 64. And this class is actually requiring you to use the ND item class for identification, right, of items inside the device code. And with this class, you are getting even more different features. So here with ND item only, you're getting barriers for synchronization between work items in the same work group. You may use the local shared memory with ND items and so on. So when the obvious question, since I said that it's asynchronous execution mode, so that once we did the submit operation, the execution of a code keep going further. So the question here is how we can guarantee that this common group submitted to this queue and finally to some device, right? But this kernel was executed. So there are different ways how you can control it, and that's why we do have the explicit additional scope here. So we are actually performing the destruction of a buffer, right? And by SYCL standard, when you destruct the buffer, then the data is guaranteed to be written back to your initial arrays. So once we destructed our buffers, we can safely access our host data, right? And print the results, for example, on the screen, or use it further in our host calculations. You cannot access your initial data directly with this buffer accessor concept before you destructed the buffer. But the behavior in this case is undefined. So you cannot write some code using the A vector here, because in this case, it will cause probably some runtime issues. But it's not the only way how to do the synchronization. So the synchronization may be different. It may be grouped into two major subgroups. So one is synchronization within kernel. As I said, there is one way to synchronize work items within a work group, and you can use barriers to do this. And you will need ND item and ND range. The other way is synchronization between host and device, right? So when you want to really double check, to be sure that and double check that the data is really back on the host and you can do further stuff, or you want to wait until some kernel is executed and so on. So there are four major ways how to do this. So there is a wait function, and it's a member function of a device queue, and it's also a function which may work on some event, because in many cases, all APIs in SYCL returns actually an event class object. If you destruct the buffer, it will also help to synchronize the data. That's what we showed in our trivial example. There is also a way to control the host accessors and the buffer accessors. The asynchronous graph is constructed under the hood and caring about the proper execution order of your kernels. So one example on the host accessor. So here you can see that we create an accessor outside of a common group scope. You see here a queue submit. So this is a common group scope. And we don't create an accessor here, but we create a host accessor outside of this. And we use a special constructor and class host accessor. So this one is a blocking call, which means we will wait until all the kernels using this buffer finish the execution. And that's why once constructed, we are safe to print some data on our host code via this accessor, because it guarantees you that all the common groups submitted to the queue will finish the execution. And as with usual, in usual case, once you construct the buffer, it takes ownership of the data stored in the vector here. And our version or variation of buffer destruction synchronization example is when you call some function, right? So here you can see that there is a DPCPP code function, and obviously once you exit this scope, it's also the destruction of a buffer happens. So that's why you can easily access the initial vector V here, because we destructed the buffer. Just here, like a spoiler of unified shared memory as an alternative to accessor and buffers. So here is an example how you can use the unified shared memory approach, and I will have more details, but since we may be limited in time, I want to show the basic concept. So instead of creating buffers, we can use spatial APIs to allocate the memory, right? There is a API called malloc device, but here we are using like implicit data sharing with unified shared memory, where we can allocate some data on the host and use this data inside the kernel code, or you can allocate the data via malloc shared, and then the data may migrate from host to device and back automatically, so you don't need to do explicit mem copy operations. So in this case, you also don't need to explicitly create a common group. It will be done under the hood for you here, because we don't need actually a common group scope here, right? We don't need accessors. That's why we don't need to define accessors in the common group scope. We can bypass it, and this feature called in SYCL standard queue shortcut, so that we can really compress our code and invoke parallel fault directly from the queue. And as you can see, we are calling a wait function here. So the reason for that is that I want to synchronize, but I want to synchronize on the event returned from a common group submission or parallel for invocation. So here actually the event is created, and you can handle this create by doing, let's say, this stuff. Okay, something is wrong here, but you can create an auto event, right? And then do a e.wait operation. So here we are doing exactly the same. So we are getting the event returned by the submit operation finally, and we are waiting on this event. If you invoke wait on the queue, when we will wait until all common groups submitted to a queue are executed, it may be different, right? Event synchronization allows you to fine-tune what exactly you want to wait, right? If you want to wait only on this specific common group and kernel, you can do this. So it's much more compact, right? But then you need to care about dependencies yourself. And this is a simplified model which is called implicit memory transfer model, but there is also explicit one where you are actually doing memcopy also explicitly. I will go back to this in a few minutes. Now I want to show you that SYCL is not error-based, it's actually exception-based since it's C++ based standard. So in order to catch exceptions, you need to use synchronous or asynchronous handling, right? Synchronous exceptions in SYCL happens immediately and detected immediately. For example, when you cannot construct an object, let's say create a buffer, and you can use try-catch block to catch this. And I think by default, it's done automatically for you. Asynchronous exception may be caused by a future failure. Note that SYCL is asynchronous-based mode, right? Which means we do qsubmit, and then some magic is happening on the backend side, right? So this, the kernels are scheduled when they are executed on the device, and much later the exception may happen, and you need the asynchronous exception handling for this case. Note that in order to catch this, you will also you need also to explicitly say when to process, right? So when to stop and check for exceptions. And to do it, there are methods called wait and throw asynchronous, and wait and throw on event. So there are 3 ways how to check for asynchronous exceptions. So a few words about what is happening under the hood. So once you created your simple vector addition application consisting of a host code and device code, right? You're invoking the compiler. With Intel, you have this DPC command which you can use in order to invoke the DPC++ compiler. It takes as an input some arguments which you want to use and the source file, right? And then actually there will be always like multiple compilers used under the hood, right? Depends, of course, but what is happening there is the SYCL device front-end compiler generates an integration header files. So when your host code, so like the majority of your code, a major part of your code will have the usual host code with some include header file, and then it's compiled with the usual host compiler, and the host object file is produced. That's it for the host code. And for the device code, in Intel implementation, we are generating an LVM IR, and then there are 2 options. So the first one, which is default, is that out of that we generate SPIR-V binary format and put this SPIR-V to the object file. So that means that when you run your application at runtime, we know the device which is available on your system, right? And just-in-time compilation will happen on this SPIR-V binary code. And the code will be compiled for target device. Of course, there are pros and cons for this concept because the overhead may be significant depending on the number of kernels and so on. If you know in advance the device on which you're going to run on devices or devices on which you're going to run your code, you can also use so-called ahead-of-time compilation flow, which requires you to specify the device, right, on which you want to use. And you can do it with these options, for example. These targets may be different. So you can use this _gen for Intel GPUs, x86 for CPUs, or even NVIDIA stuff, NVIDIA CUDA to target NVIDIA devices with open source compiler. And note that once we compile the code and running it, since SYCL is an abstraction, you will have some kind of a multi-layered pie under the hood, right? So you have your SYCL application, which may have a device native ISA or SPIR-V binary, which will be compiled at runtime to the native device instruction set. And you have a SYCL runtime or DPC++ runtime, which cares about scheduling of your kernels in the proper order, doing the memory management and a lot of our stuff. But on the lower level, we will finally go to some kind of native runtime, which can be OpenCL runtime, which can be level 0 runtime. So it should be clear that under the hood, this abstraction will be switched to a real low-level set of API calls. So it will be finally OpenCL application, right? It will be level 0 set of calls. It will be CUDA for NVIDIA hardware or HIP for AMD and so on. So important thing maybe that for CPU, we are using OpenCL implementation. And you can see here this OpenCL runtime actually using a TBB, Intel Trading Building Blocks runtime to map properly these work groups, right, to real CPU threads and execute it on CPU. Note that at runtime, you can control which backend you want to use and on which device you want to run. And it's possible because we have this additional layer called plugin interface layer. So it's finally a set of stub functions, right, which we are going to dispatch at runtime. So it's a set of API which called with PI something, let's say PI malloc device, which will become ZE malloc device if we want to run on level 0 runtime, or which will be CL something for OpenCL, or CUDA malloc for CUDA, and so on. So again, in order to hide the implementation details, you need to pay this cost, but the overhead usually is relatively small. And we have a environment variable to control where you want to run. So in the simplest way, you can just set this environment variable to GPU. And if you use default selector to construct a queue in your code, then the runtime will pick up the GPU for you. But you can even list all devices with this SYCL-ls command, which is shipped with one API toolkit package. And there you can actually get all the devices available numbered, and you can even just say 3. SYCL device filter equal 3, or you can say SYCL device filter equal level 0 or OpenCL, which will limit you to pick up only OpenCL or level 0 devices. Yeah, since I promised that we will talk a bit more on unified shared memory, again, older SYCL standard didn't have this unified shared memory feature, and it has only buffer memory abstraction, which is powerful way of expressing data dependencies, but it's maybe not the best way, which may be used while you're moving, for example, from CUDA, because a lot of code rework will be required. And also replacing all pointers and arrays with buffers will also require a lot of efforts from a developer. So unified shared memory provides a pointer-based alternative, which is a bit more usable when you in porting the code to the accelerator. And also it gives you a better and more explicit programmer's level of control, right? So the idea is that the pointer which you create on the host side will be the same on the device side. It doesn't mean that you don't need to memory actually finally transfer the memory back and forth. It's, for example, okay on integrated graphics for Intel CPUs because it's actually the same memory available for CPU and GPU, but for no, it's like a corner case, I would say, of integrated graphics. Usually you need to transfer data, and there are different modes for managing the memory. So there is an allocation type called device, host, and shared, and depending on the allocation type you are using, you are getting the different behavior and different features. So This is an example of an explicit data movement mode, which I have not shown previously. So here you are directly allocating the memory on the device from the host side. When you're doing the mem copy operation, so you're actually copying this host array to this device array on the device, right? You're waiting until this operation finished, because mem copy is one of the rare APIs in SYCL, which is, it's actually, as usual, the asynchronous operation, right? So there are very rare operations which are synchronous, like wait, for example, but mem copy is asynchronous, and it's different from CUDA. So you need to wait here, or you can, it also return actually an event. So what you can do is you can invoke wait right here, which may be even better, like this. So when we are doing the qsubmit operation, again, there is a feature which is simplifying it, so you can just write q parallel for, and it will work too. You need to wait until this code is actually executed on the device and copy the memory back. So here you can see you're controlling the moments when the memory copy operation is happening, right? You need to do more in your code, but finally there are more possibilities for performance improvement with this concept, because you may leave the data longer if you know that you don't want to transfer it back and you want to reuse it on the device. This sometimes can give you a better control. And there is implicit data movement mode, which I showed already earlier as a spoiler for your unified shared memory. And you can see here that actually we are using malloc host and malloc shared, and then we don't need to do explicit mem copy operations. The runtime will do mem copy operations itself, but we don't have control when it will happen. Okay, so now I want to go to this EasyWave example. So it's a quite interesting code, which is a stencil code, which was written in OpenMP and CUDA initially. So there were two implementations, one for CPU and one for GPU accelerators. It's not really large code. It's relatively small, I would say, code. And we've been working with ZIB, TUS Institute of Berlin, on migrating this code to SYCL, and almost all the migration was done by DPC++ compatibility tool, which Intel provide, and also open source recently, to simplify the process of migration from CUDA to SYCL. So this tool, we migrated the code to SYCL, and finally this code, this version of the code, which is open source now, was successfully running with quite reasonable performance. So let's say that the performance on NVIDIA GPU was 5% less than native implementation in CUDA. And so we were running the same code on Intel CPUs, GPUs, FPGA, NVIDIA GPU, and AMD GPU. And again, the performance was reasonable on all these devices except FPGAs, because of course, functionally we were able to run it, but for FPGA, you will require additional fine-tuning since it's so different architecture. So that's it from my side for today. I hope it was useful and interesting for all of you. I also collected a set of useful links which you can follow. So it's, again, the links to all Intel open source project, to the compiler, graphics, computer runtime, and graphics compiler too. And then there are very nice documents on the SYCL itself, where you can find much more details, like the book written by our evangelist James Reiner, in close collaboration with our folks and engineers, and also this one API GPU optimization guide, which can be useful. And on Intel Dev Cloud, you may find a lot of training materials and all the hardware and software pre-installed and ready for use. So if you follow this link, you will find a resource where you can get access in just 1 minute, where you have the latest hardware available by Intel, including Ice Lake processors, including integrated graphics machines and discrete graphics machines too, which you can use for free to try one API and SYCL there.